Hi everybody. We really have finished talking about chapter 16, but tonight I know you're doing some practice problems, so I thought it might be a good idea to refresh a little bit. Chapter 16 is where we start to talk about random variables, and a random variable, of course, is a value that gets its value as a result of the outcome of some random event. And we can have discrete random variables and we can have continuous random variables. There are a lot of ways that we could use to describe discrete versus continuous, but if you want to be quick and easy, you can think of a discrete random variable is a random variable where all of the outcomes can be listed. And a continuous random variable is one where the outcomes cannot be listed. Now that's not to say that you can't have a notation to show them, it's just you give them the values in interval form instead. Okay, so that's going to bug me, sorry. A probability distribution will always show all of the possible values of the random variable, but also the probabilities. So we just kind of make a table of the random variable x, and we show all of the x values, the first x value, which is not x sub I, which is x sub 1. We show the second x value, and we show the third, and all the way up to x sub I. We also, though, show the probabilities of x, and that'll be probability of 1, sub 1, probability sub 2, probability sub 3, all the way up to the probability of I. And that's how we show the distribution. But we can also find the value we expect to get for a discrete random variable. And we can calculate it using this formula, which really pretty much says, right here, this formula, which says I'm going to multiply the value times the probability for each of those possible outcomes, and I'm going to then go ahead and get that value. This is also called the mean of x, or mu x. Now this mean of x is really helpful to us, but because what it really does is it shows us what's happening in the long run. And so if we ever describe the mean in context, we really want to say, in the long run, we expect an average of, and then whatever that random variable would be. The variance is calculated really almost the same way, except now we're going to use the mean. So now we're going to subtract the mean from each individual value. We're going to square that value and multiply that by the probability. Obviously, once we have our variance, we can find our standard deviation, because the standard deviation is just the square root of variance, so it's going to be the square root of that formula. So it's a lot easier to calculate the variance first and then just take that square root. So let's look at an example. If we look at the first example and we consider the number of tails when we're tossing 3 coins, there are actually 4 different options here when we're tossing 3 coins. First off, we could get no tails, we could get 1, we could get 2, or we could get 3. Then we're going to go ahead and calculate the probability for that. The probability of no tails would be 1/8. The probability of 1 tail is 3/8. That's a 3, sorry. Try that again, 3/8. The probability of 2 tails is also 3/8. And the probability of 3 tails is 1/8. I'm going to give you the mean and the standard deviation for each of these as we go along, so you might want to pause and then come back and check. So if you pause now, and then you can just calculate the mean and the standard deviation, and you can come back and check your answers. But the mean is equal to 1.5 tails with a standard deviation of 0.866 tails. What that means is, again, over time, we can expect to get an average of 1.5 tails when we toss 3 coins. Let's look at another example. If we want to consider the value of one roll of a number cube, we could potentially get a 1, a 2, a 3, a 4, a 5, or a 6. And the probability for each of those is going to be 1/6. And we could go about using our formula from the previous slides and calculate the mean of the value of one roll and the standard deviation. So I'm going to go ahead and give you the answers, but you might want to pause now, get your answers, and then come back and check. Okay. So the mean number that we would roll on a number cube would be 3.5. And the standard deviation, and that's obviously pips or whatever you want to call those numbers on the die, number cube, 1.7078. That's what we get for our standard deviation. So a constant will absolutely affect the mean. If we are multiplying the distribution by a constant b,
Ms. Lutz, give a call.
again, if we multiply a random variable x by the constant b, and we know the mean of the original distribution, then we can simply multiply that by b. And if we are going to multiply the distribution, the random variable, by a constant b and add a constant a to each of those values, then that works out the same way. We're going to take b times the original mean and then add a in. Doesn't work exactly the same way for variance and standard deviation, though. For a constant may affect the variance and the standard deviation. So for instance, when I multiply my random variable by b, my standard deviation is multiplied by b squared. I'm sorry. Did I just say that? Let me go back. A constant may affect the variance and standard deviation when I take a random variable x and I multiply it by b. When I find my variance is b squared times the original variance. That means that our standard deviation of bx is going to be b times the standard deviation of x. And that kind of makes sense. That goes along with what we've done before in terms of mean. But then when we take the variance, when we take our random variable x and we multiply it by b and then add a to every single value, that does not hold true, because if you look at the variance here, the variance then becomes b squared times the original variance. Notice that we're not adding a in, and that's really because variance and standard deviation are both measures of, again, variation, so they're measuring how things are related to one another. So the standard deviation of bx, gosh, this is really, I need a better pointier thing here. Bx plus a is really going to be equal to just, again, b times the standard deviation of x. Okay, let's look at our examples. So, if we have our examples, and remember that x stood for the number of tails we would get when we toss 3 coins, and y was the number we would get when we roll our number cube, we can do a few examples. For instance, suppose that we would win $2 for every tail that we toss. If we were going to win $2, then we would say mu of 2x. And we could get that. That would be 2 times 1.5 which is 3. On average, we would be winning 3. And our standard deviation of 2x would work out the same way, and we would get 2 times 0.866. Now, why is that? That's because the variance, right, the variance, whoops, of 2x is going to be equal to 2 squared times the variance, which was, 0.866 times squared. Nope. 0.866. Yes. 0.749956. Doesn't feel right. But it would be this one. Okay, so then the thing is, though, if we then say, okay, well, what if we have to, we'll win these values, but we're going to have to pay $1 to play. So then we'd be finding the mean of 2x minus 1, which would be 2 times 1.5 minus 1, which comes out to be 2. That's not a big deal, but when we want to find the standard deviation of that, this would be 2x minus 1, which we're going to have to go back and look. That's going to become the variance, which is b squared, or 2 squared, times the standard deviation squared, which is our variance. And notice that the plus 1 does not go along for the ride. And we'll still come out with 2, 3, 7.1, so 1.732. Okay. Sometimes we combine random variables too. And as long as they're independent, we can find both the mean and the standard deviation and variance. If they are not independent, we can find the mean by combining them, but we cannot find the standard deviation. So let's just consider what would happen if they're independent. If they're independent and you want to add 2 random variables together to make one larger random variable, but you already know the means of each of the individuals, each of the individual random variables, you can simply combine them together. And so, for instance, when we had mu of x was 1.5 and mu of y was 3.5, if we want a mu of x plus y, this would be equal to 1.5 plus 3.5, which is 5. Let's go back to blue. And then, for standard deviation, not quite as easy, but we can do the same thing. If you recall, the standard deviation of x was 0.866, and the standard deviation of y was 1.7078. So if we want the standard deviation of x plus y, it's going to be a tight squeeze. It's going to be the square root of 0.866 squared plus 1.7078, oh gosh, squared, which works out to be, I'll tell you in a second, works out to be 1.9148. I hope these examples kind of helped you. I know that the practice problems from chapter 16 are what you have for tonight's homework, and so hopefully you can use this. All right, thanks so much. Good night.